Okay, guess we can get started. Do we have any questions before I go through the final? Nothing? Good? All right. All right. First thing you got to know are significant figures. How to count the correct number of sig figs. Any questions? Do you want any examples?
Yes.
Okay. So if we have, let's say, 0.0005708200. How many sig figs are in this number? Parker says 8. What do you guys think? What?
I think
8?
9.
9? Well, let's see. So first of all, the non-zeros are significant, right?
Yes.
And the zeros between significant figures are also significant. Okay. What about these zeros to the left? Are they significant?
Yes.
They are not. Why aren't they?
We
They're
only start-
just placeholder zeros.
Yeah.
They just tell you how big or how small the number is. That's it.
We
Okay?
only count after the first significant.
So zeros to the left are not significant ever. Okay? What about the ones to the right?
Yes.
They are only significant if what?
If there is a decimal
If
point.
there is a decimal point put in the measurement. So yes, they are there. So there's 1, 2, 3, 4, 5, 6, 7, 8 of them. 8 sig figs. Questions? Okay. If we have 3 eggs, how many sig figs is that? Infinitely many. Why? Because it's exact. Okay? Exact or counting number. What about 3 inches? How many sig figs does 3 inches have?
1.
1. Is it exact?
No.
No. The way we measure inches is never exact. Always have an estimate, right? Okay, so there's infinitely many right there and 1 sig fig right here. Okay, any questions about counting sig figs? How about the rules for multiply and divide, add and subtract? Are we good with those, or do we need an example? Okay. So if we do, let's say, 3.1 multiply, let's mix them up a little bit. Add 4.397 multiply 4 divided by 2.629. Okay, so now we have to think of how would you do this mathematically? Order of operation, right? So what do we do first?
What's inside the parentheses?
Inside the parentheses, we add those guys. And what do we get? Without rounding, what do you get? Don't round until your final answer.
7.97.
7.97. 497. 7.497?
Yeah.
Okay. We're good? Now, if that was all we're doing was adding those two, where would we round it to? What? One decimal place, right? This is one decimal place, this is three decimal places. We go at the least
7.5.
7.5, and we're just going to leave that in the cloud, right? When I say the cloud, I'm just saying just somewhere we know, right? We're not going to use that. That's just counting sig figs. That's all. Okay? So we're not going to use it. We're just going to leave it there for a minute. Now let's, once we get that answer, what do we do next mathematically? Multiply by 4. So what do we get when we multiply by 4?
29.988.
29.988. And on the bottom it stays the same, 2.629. But what's going to be up in the cloud here? What should this be? What should we round it to according to this multiply this?
30?
30, right? 1 sig fig and 2 sig figs. So we go at the lowest, which is 1 sig fig. And 30, since there's no decimal place, that's 1 sig fig, right? And so now we do 30 divided by 2.629. And what does our calculator give us? 11.406.
Wait, is that with the 29 number or with the 30?
Well, we have to do this number. Yeah, sorry.
Oh, okay.
Not 30. My bad. You're right. So we don't round until the very end. So 29.988 divided by 2.629. Is that what you got?
Yeah, it keeps going.
No, that's okay. We're going to be rounding it anyway, right? Okay, so we're going to round it to what?
Is it still at one decimal point? Or is
That's a good question. What are we doing here in this last step?
it, oh, there's a lot still.
We're dividing, right?
Yes.
So dividing, what rule do we use for divide?
4 sig figs.
The lowest number of sig figs. So how many sig figs is going to be in our answer? 3 or 4 or 1?
1.
1. Why 1? Because this top number should only have 1 sig fig, right?
Yes.
Because when we multiply this to this, that tells us we should have 1 sig fig. You with me? And so our top answer is 1 sig fig, and our bottom answer is 4 sig figs. We've got to go with the lowest number. And so we should round this to 1 sig fig.
Which is 11.
That has 2 sig figs. 11 has 2 sig figs. 10. You might say, well, that's wrong. It's not even that. So what do you mean? Why do we do this?
So that we don't overcalculate. It's getting as close as
I understand what you're trying to say. A little different words. Let me change the wording. I think what you're thinking is right. So you can only be as good as your weakest measurement, right? And so if we just kept it three decimal places and then just kept it 3 decimal places, then we might say that's our answer, but that's not even close. This number could be what? 3.5 or 4.4, right?
4.75. We don't know.
So it's kind of far off. This one isn't very significant at all. And so that's what we have to go with. That's our weakest. And don't just find the weakest or the lowest amount of sig figs and go with that one. You got to follow the order of operation and stick with that. But are we good?
So if it was still like 15, it would be going down to 10 anyway?
No, because 20 is closest to.
Okay, Okay. So 14
Because 5 or higher, yeah.
goes up.
Uh-huh.
And then, okay.
That's right.
Okay.
Does that make sense to everybody? Question? No? All right. Any other questions about significant figures? We're good with that? All right. Dimensional analysis is the next thing you got to know. I started grading some of the e-portfolio assignments. And there are some that were not using dimensional analysis. Make sure you use that. Why? Is that because that's the way we do in chemistry. If you don't do it my way, then get out of here, right? No. It's my way or the highway? No, that's not why. Why do we use dimensional analysis?
Make sure we get the correct number.
Make sure it's correct. Because if we're going to give somebody a prescription, or we don't want to just round wrong and overdose them, right?
Mm-hmm.
It's got to be. Now, in everyday living, not a huge issue with, dimensional analysis is, you still want it right. I guess I was thinking sig figs, never mind. Yeah, it's a big deal. Dimensional analysis is just to make sure you get it correct, okay? So, if we're looking for the density, should we just use the density formula? Did we learn anything from the midterm? Let's say we have a piece of gold that has a mass of 49 kilograms. And it has a volume of 3 centimeters cubed. This is probably way wrong, but okay, I'm just saying, okay. And we want to find the density in grams per milliliter. And how do we know it's grams per milliliter? Because the multiple choice says grams per milliliter, right?
Centimeter cube is equal to milliliter.
What?
1 centimeter cube is equal to 1 milliliter.
That's right. So, but here's what I'm getting at. If we use the density equation, density equals mass over volume, right? Oh, here's the mass and here's the volume. Can I just do 49 divided 3 and call it good?
10,000, the unit in grams.
That's right. You've got to make sure it's in the right unit. So it is okay to use that. Just make sure you include units. We're not there yet, so we keep going. So we go 1 kilogram to 1,000 grams, right? That goes away. And 1 centimeter cubed is the same as 1 milliliter. So that goes away. And now we have grams per milliliter. So we're done. We can multiply and divide. But let's say we don't know that formula. Can we just do, so we're looking for grams per milliliter. Is it good to know that's a unit of mass? Yes, it is. Is it good to know that's a unit of volume? Yes, it is. Okay, we want that. Okay, so I know I have kilograms. So I can go to kilograms to grams. If I want, I can just do kilograms to grams, just right there. And I get 49,000 grams. And then I need milliliters on bottom. So I go 3 centimeters cubed, 1 centimeter cubed on bottom to cancel to 1 milliliter. That goes away. Oh, and I get 3. So divided by 3 milliliters. Now I have grams per milliliter. Either way you do it, the math is the same. Are we good? So use dimensional analysis, meaning you have to use your units. Include all of your units. Get the units you don't want to cancel out until you got the units you're looking for. That's why it's so important that your first step is what's the question asking and with what units? And then what do you know with what units? And then go from something that you know. Don't ever start with something you don't know. And that's dimensional analysis. And there's a couple problems with dimensional analysis in it. But it doesn't matter what it is, whether it's density or a dosing problem or just a general stoichiometry problem. They're all the same. Are we good? Did I beat that to death yet? All right. Are there any particular specific questions on dimensional analysis? Do you need to do a dosing problem? How are we feeling? Good? Okay. All right, next. We got to know if we're given an isotope in this form, we got to know how many protons, neutrons, and electrons there are. And we do this. So I will give you actual numbers, right? Do you want an example? How are we feeling? Yeah? Okay. So let's do copper. I don't remember the numbers, so I'll just pick a number here. 70. Copper is number 29? I'm guessing. It shouldn't be. All right, let's say it's 2 plus there. How many protons does copper 70 have? You looking for me?
Mm-hmm.
Thanks. Is it number
29.
And what's the mass?
The mass is 63.5.
Okay, good enough. That's just a different isotope. Okay, so how many protons do we have? 29 protons. Because that's this number down here, right? Number of neutrons, how do we figure number of neutrons?
29 minus 7, or 70 minus 29.
70 minus 29 gives us the number of neutrons, which is 41. And electrons, are there 2 of them?
27.
Yeah, what does this tell us? There's more what?
Two fewer electrons than there are protons.
Those 2 electrons.
Yeah, that's right. It's 2 plus. That means there's more positives, right?
Right.
More protons, 2 more protons. So this number's 2 bigger than this number. So 27, that's correct. Are we good? Do we know about isotopes? What's the definition of an isotope?
Same atomic number, but different mass number.
Same atomic number, different mass number. Yep. So what does that mean?
Different neutron, another neutron.
Yeah, same number of protons, that's the same atomic number, right? And different number of neutrons, so different mass. Good? So if I have this right here, and I have a bunch of these, they're not all the same. I just find the ones that are the same on the bottom number, right? And different top number. Those are isotopes. Good?
Wait, so could you repeat that last one? Same top number, different bottom number?
Same bottom number, different top number. Does that make sense? The top number is the mass, so that's protons plus neutrons. And the bottom number is the number of protons. They've got to be the same. Can those ever be the same isotope or different isotopes? Why not?
Yeah, different.
Different elements, right? Different number of protons. Okay? All right, can you convert Kelvin to Celsius, Celsius to Kelvin? What's the formula?
Will you be giving us the same reference sheet that you gave us for the midterm?
Yep.
Okay.
What's the formula? Go ahead.
Kelvin equals degrees Celsius plus 273.50.
And if you're looking for degrees Celsius, then it's this, right? You have to memorize both of them?
No.
No. You could just subtract this to both sides and you get this one, right? Are we okay with that? Do we need to go through an example? I don't want to waste your time, but I want to make sure you got what you need. Okay? Can we convert metric to metric? So, for example, converting from micrometer to megameter, for example. Can we do that?
Could go into that one.
Yep, sure can. Let's say we have 2 megameters. Let's go the other way around. 2 megameters, and we want to convert that to micrometers. Where do we start? I'll give you a hint. It's not with what we don't know.
It's what we know.
Oh yeah, what do we know? 2 megameters. Do we know how many micrometers there are in a megameter? If you do, you can use it, and it's just one conversion. But I didn't give you that. So what do you know? Megameter to what? To meters. So megameters goes on bottom, and just meter goes on top. You with me? Okay. Now what's the conversion? How many meters are the same as how many megameters? We have to know this. And this I will not give to you on the exam. You have to, so if you don't have that reference sheet, if you don't have that on your reference sheet, you might want it on there if you don't know it. All right. Which one's bigger? Mega or regular? Mega. So we'll say for every 1 megameter, how many meters?
10 to the 12th.
1 million, or 10 to the 6th power. If you don't have that memorized, I suggest you write it on your reference sheet, okay? Or we can do, instead of that, we could do 1 meter to 10, no, that's how we'd do it. We'd do 1 megameter, 10 to the positive 6, right? Either one, okay? So that goes away, and we're not to micrometers yet, so we keep going. Meters to micrometers. Which one's bigger? Meters. So for every 1 meter, how many micrometers? 10 to the what? 10 to the minus 6 micrometers. So there's a couple ways we can do this. Micro means 10 to the negative 6, right? So we can say 1 micrometer to 10 to the negative 6 meters, because those are the same. You have to do it that way. Or
0.
we could say for every 1 meter, that's 10 or 1 million micrometers. Do it the way that works in your brain. Because 10 to the negative 6 means 1 over 1 million, right? 1 millionth. So how many 1 millionths is equal to 1? 1 million 1 millionths is the same as 1, right? Do you have a way stuck in your mind that works? Or do you have a question on that? Okay? So meters goes away, leaving us with micrometers. So we have 2 million. What's that?
2 into 10 raised to the power 12.
That's a lot, right? So what is that? 2 trillion? 2 times 10 to the power of 12 is 2 trillion, yep. 2 trillion micrometers.
I have a question. So when I put it into my calculator, it spits back 5E11. So should I just try doing it by hand? Or is
5E11?
yeah, or is there a way to convert it into a real
How did, well,
I
always,
think by E they mean like scientific notation.
that means times 10 to the 11,
Oh.
but I don't know how you got 5.
So it's 1 million divided by 2 times 1 million divided by 1.
Okay. Where's the divide symbol in this work?
The bottom parts of the
Right
equation.
there, right? Is there a 2 underneath those lines? No
I
2s.
was mistaken.
So and guys, doesn't matter the way I do it. You got to find a way that works for you and that works. Okay. If you want to put a 1 underneath there, then you can multiply all the tops and get an answer. Multiply all the bottoms, get an answer, and then divide the 2. Always, that way always works. The way it was taught in elementary school still is true. Okay. The way I do it, just because it's simpler for me, I type in what I'm given, 2, and then I multiply, because it says multiply, everything that's on the top, divide everything that's on the bottom. Done. Are we good? Did that help? Okay. Okay, alpha decay and beta decay. Alpha or beta decay. It's one of them. I'm not going to tell you which one it is. So what's an alpha particle? What's the symbol for an alpha particle?
A?
Not quite. What? It's 4-2He, right? And what's the symbol for a beta particle?
Electron,
Well, and what's the mass of an electron?
0.
And what's the charge of an electron? -1 E, right? All right. And so you'll be given, you might be given something that says, okay, we have, let's say we have hydrogen 3 undergoes beta decay. What am I going to, and I want to know the product. That's what the question might say, right? So it undergoes beta decay. Decay means it comes off. It's one of the products, right? So beta is right here, 0, -1 E, and what are we left with?
Helium,
We start with 3, we get rid of 0, we end with 3, right? Or another way to do it is 0 plus 3 equals 3. You with me? Get rid of all those markings. Do the same thing here. This is 1, has to equal -1 plus what?
2.
2. And what does that tell us it is?
Helium,
Helium. It's an isotope of helium. Are we good?
So the thing next to hydrogen is not the protons.
What do you mean?
Oh, because of the negative, it gains a proton.
Well, because -1 plus 2 has to equal 1. The bottom numbers, right?
So the H31 is after it underwent beta decay? Or is that before?
No, we start here, and we get beta decay with something else. So what really happens is you have this nucleus,
Yeah.
and a beta particle pops off. And when that pops off, it's left with something else. It's no longer hydrogen, it's helium.
Oh.
Why? Because these numbers work out. You start with 3, you have to end with 3. You start with the charge of positive 1, you have to end with a charge of positive 1. Does that make sense? Or no?
Not really. So my question is, did it gain a proton? Did it keep a proton? Or did it lose a proton?
Here's what happens. Great question. So we have this, what's the nucleus of helium made of? Has 1 proton, let's say the red is proton, and then it has 2 neutrons, right? That's what it looks like before. And then what happens is a little tiny electron comes off of this, comes off the neutron. Neutrons are neutral, right? If you have 0 and you get rid of a -1, what's the charge? What's 0 minus a -1?
1?
Positive
Positive
1. So that becomes a proton. That neutron turns into a proton. That's what is happening.
Oh.
So this right here is just a math way of how to tell what numbers are what.
So yeah, the thing came off and the neutron became a proton.
Yeah, because it lost a negative charge.
Right.
Does that make sense? Thanks for digging deeper. If you want to know, you got to dig. Sorry. Sometimes I try to keep it simple, and yeah, if you want to know more, just keep asking.
And is the top number the one that we use to figure out the element?
The bottom number tells us what element it is. So
The
since
top
this is a
number.
2,
Okay.
that's the atomic number 2, that's helium. Yep, good question.
And the atomic number is the atomic mass. That's why it's a 3. It's because it has 2 neutrons.
Because it has 3 nucleons. Has 2 protons and 1 neutron. That's a mass of 3. Because remember,
Okay.
protons and neutrons have the same mass.
So
Okay.
were there 2 neutrons in it before that then transitioned into the proton?
That's right. This has, so if you look at this, so just in the problem before, we have 3, 1H. How many protons does that have?
1,
How many neutrons does it have?
2.
3 minus 1 is 2, right?
Oh,
Yeah.
Oh, okay.
Are we good?
Yeah.
Can you do it with alpha decay? Do you want another example? Okay. So let's say we have uranium-235. Undergoes alpha decay. That's what it's going to look like, right? Because 4,2-He, that's an alpha particle. And so here, we're just getting rid of 2 protons and 2 neutrons, right? Because that's all alpha particle is, 2 protons and 2 neutrons. So this nucleus gets rid of 2 protons and 2 neutrons. And so now what is it? It's 90 because we have the 92. That has to equal 2 plus 90, right? That tells us it's thorium on the periodic table. And then 235 subtract 4 is 231. Are we good? So if you're doing it the math way, then just make sure you do the math. And if there's a negative, you got to count that negative, right? All right, any questions on alpha and beta decay? Okay.
say we have, magnesium and, it goes through beta decay,
Okay, so magnesium,
or an
Is-
isotope of.
is that
magnesium.
12, right?
Yes,
And 25, let's say?
yes,
Beta decay is still 0, -1e.
yes. So it goes through beta decay.
So you tell me what we get.
So does it end up with,
What number on top?
25 on top
Good.
and then 13 on bottom?
Well, let's see. It sounded like a question when you said 13, so let's figure it out right here. Watch. -1 plus 13, is that equal to 12?
Yes? Hold on.
Yeah, double check.
Yes.
Okay, then that's right. And if it's not right, then it's not right.
Oh, okay. Yeah.
Then you got to change the number. And so what is 13?
13 is, aluminum.
Good?
Yeah.
That's it. Any other questions on that? All right. Next thing you got to know is tell the difference between homogeneous and heterogeneous versus pure substance, right? So mixtures versus pure substances. How do you tell if something's a pure substance?
If it's made up entirely by one thing. Oh,
A little bit more information than that. Two types of pure substances that we talked about. If it's an element, there's 118 different elements. If it's one of those guys, it's pure. Okay? What else? If it's a compound, like H2O is pure. If it's pure H2O, right? Okay? Can you have a mixture with water and something else in it? Yeah, you can, but if it's just H2O or just CO2 or just a compound, it's pure substance. And if it's not an element or a compound, it's a mixture. And it can either be homogeneous or heterogeneous. Okay, so I'm going to give you a few examples. And I would write these down. I have the test right here. I'm looking at it. Okay. Helium. What is that? Homogeneous or heterogeneous?
pure substance.
Good. It's a pure substance. Is that what the test is going to look like? Is it going to try to trick you? No, we're not trying to trick you. If you know it, it's not a trick. Okay? But that's what it's going to be on there. There's going to be elements on there that are not homogeneous or heterogeneous mixtures. Okay, what about air? So helium was pure substance. What about air?
Homogeneous.
Why homogeneous?
Because it's not like there are separate things of water, helium, oxygen, CO2. They're all mixed together.
So it is a mixture. Why isn't it heterogeneous?
Because it's thoroughly mixed. If you reach out and grab a bunch of air, you're going to have the same amount of air in your hand.
Yeah, you don't have to go over to here to breathe better, right? It's going to be the same. So that is homogeneous. What about concrete? Homogeneous? We know it's a mixture because it's not a compound and it's not an element, right? So is it homogeneous or heterogeneous? Why? Yeah. Have you ever saw it poured? If you look at the sidewalk, it might look homogeneous, right?
But there are rocks inside.
But as time goes on, it starts to break up, and there's big old chunks of rock, different sizes, right? So that's heterogeneous. What about blood? Oh, I used a different color. Oops. What about blood? Looks pretty homogeneous, right? What about raw milk? Oh, it separates. Homogeneous mixtures don't separate. Okay? So blood is heterogeneous. Can you separate the blood?
Yeah, in the centrifuge.
Yeah. Are we good? And what about salad?
Heterogeneous, 'cause just a bunch of big chunks.
Okay. Can we do this, guys? Okay. You guys wrote those down, right? Okay. All right, next. You got to know the scientific notation for all the prefixes. If you have them on your reference sheet, you don't have to memorize them. But gosh, probably a good thing to memorize them. But if you want to make sure and do well on the final and you don't have it, then just put them on there. Do we have any questions on those? Because I can tell you some right now, and if you don't know them, you're still not going to know them. You either have to have them or you have to know them. Either way, you have them, right? Okay. So make sure you know that. So prefixes, scientific notation, like what does centi mean? Like centimeters. What does centi mean?
1,000.
10 to the -2. That's what you need to know. Is it just centi? No, you need to know all of them. I didn't give you the one that's on the test. Maybe I did. I don't know. Okay. Okay, next thing you got to know is electron configuration. That's like the 1s2, 2s2, 2, right? Do we got this, or do we need to do an example? You tell me. Good? If you need one, yeah.
Can we go over like the orbitals,
Yeah.
Uh-huh.
like subshells and stuff like that?
Yeah, so let's do what? Let's just do chlorine. Okay, so first of all, let's do the electron configuration, because if you know the electron configuration, then the orbital diagram's basically the same, right? So what is it? Everybody get your periodic table out, and you tell me what it is. I'm not going to write it until you tell me.
2s2.
We're always going to start with the lowest energy level.
1s,
1s2,
2s,
1s2, right? There's so for every element, the maximum amount of electrons to be on that first energy level is 2. The only one that doesn't have 2 is hydrogen, right? So they're all going to have 1s2 except for hydrogen. And then what's after 1s2?
2s2,
2s2, then 2p6, then 3s2, then 3p5. And we're done. Questions on that? Can we all do that? All right. So the orbital diagram is, well, for S, there's only one orbital, right? Because there's one orbital for every 2 electrons. That's 2 electrons, and it's 1s. So we got 1, 2, up and a down. 2s, also s, so it's just one orbital. We got 2 electrons, an up and a down. Next one is 2p, and p has how many orbitals? Because it's 6 divided by 2 is 3. 1, 2, 3, that's 2p, has 3 orbitals, 1 up in each of them before you pair going down. There's 6. And we got 3s, just one orbital, up and a down, 2 electrons. And then 3p, 1, 2, 3 for p again. 3 is just the energy level. You with me? Question?
So that's the order. Wait, where did that one come from? Just the 1s again, the second one?
Right here,
No, the last one.
the 2s.
We're sorry, the fourth, your fourth one right there.
Right here?
Yeah, where's that?
That's the 3s, sorry.
3s, okay.
Right here. Bad handwriting, sorry.
Yeah.
Are we good?
So let's say we're doing chromium.
Well, let's finish chlorine
Oh,
first.
yes.
We got, whoops. We got 5. 1, 2, 3, and then pair them down 4 and 5. Right? Using Hund's rule to do
Left with only one arrow, it should be on the top.
that.
It should face towards top.
So if there's one arrow
Yeah,
on the P,
yeah.
so if there's one arrow on the P, it's just that. Yep, the up arrow.
So
Is that your question? Okay.
arrows that do not have a downward one should always be facing up. Single,
Uh-huh.
or if it fills a single
And
point.
in all reality, is this the way they look?
No.
No, it's not. This is just something that we come up with. And why do we do up before down? I don't know. Who is up a more positive direction than down
I suppose.
in general? Okay.
Oh, no, not.
So, I mean, it doesn't really matter. If you want to do downs first, great. I'm okay with that, right? But that's just what everybody else does. Goes up first and then goes down. Good?
So hypothetically, we're doing chromium. For 4D, do we do 4 blanks or 3?
So chromium is number what?
24.
24. So we got 24 electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? And then
It's like a 4F1,
3d5.
5.
Or, okay, yeah, this is one of those exceptions, right?
I think 4F.
It's in group 6. So yeah, this is 4s1 and 3d5 instead of the 3d4.
And then for the orbital diagram, would,
It'd be all the same.
okay,
So this is 4s, so this is all the same as this, right? So I'm not going to redraw that. And then 3d, so that's 4s. And then 3d is 5. 1, 2, 3, 4, 5. And we got 1, 2, 3, 4, 5. And do you see why it would rather have all of those have 1 in it instead of just 1 off, right?
because each orbital needs an up and down.
If they're going to be paired.
Yeah,
But that is more efficient to have it like that than to have it like this. 1, 2, 3, 4, 5. So you go 1, 2, 3, 4. And then have this 4s. Whoops. I did that wrong. There should be a 1 right there, right? So this is more favorable than this.
because the 3 is of a lower energy level, and it wants to be closer to the
it wants to be
nucleus.
balanced. And if it's all spread out and it's going in a circle, because they do that, then it's going to be more balanced.
Right.
And this is just on the very edge, so it's, I mean, yeah, no one's going to be perfect, but
Yeah.
are we good?
Mm-hmm.
That's why there's exceptions on group 6 and group 11.
We need to do the same thing with copper, right?
Copper, So group 6 and group 11.
So, do the whole group?
The whole group. Any of them in that group. Good? All right. Let's say we have Fe2x3. And no, that one's going to be rough. Let's give you an easier one. Let's say we have, can I see your periodic table real quick?
Do you want the other one? It's by element type.
No, that's okay. Let's just do this. Ca X. Okay? So we have a compound CaX. Is this an ionic compound or covalent compound? How do you know it's ionic compound? Because it has a metal in it, right? Okay. So let's say we have this, and X is a nonmetal. Or no. Let's say X is, obviously it's a nonmetal. X is a gas at room temperature. What is this? What is X? You have an idea? Go ahead.
Oxygen.
Is it oxygen? How do you know? Can you tell everybody how you know it's oxygen?
Because calcium has a 2+ charge.
Oh yeah. Remember doing this, guys?
Mm-hmm.
Let's find out what the charge of X is, right? Is that what you did?
Yeah.
Okay. We know calcium is 2+. It's in group 2, so it's 2+. There's only one of them, so it's positive 2. That means this side has to be negative 2. And there's only one of those, so it's 2-. It's a 1-to-1 ratio. Good. And it might not be that easy on the test, but it's that easy, right? Okay. If you know this process, it's not that bad. So that means it's X 2-. And where is the 2- group on the periodic table?
16.
In group 16. And you find which one of those is a gas. What if it says it's a solid? What if it says it's a liquid? Ugh.
All of them in group 16 are, no, they're cacogens.
Yeah, but how do you know if it's a solid or a gas or a liquid? Gosh. Should we go over some of these on the periodic table? Can I see this periodic table again?
Yes, of course.
All right. What do you think? Carbon. Solid, liquid, or gas? Why solid? Yeah, but it doesn't say whether it's a solid, liquid, or gas. It just says it's whether it's a metal or non-metal or metalloid. So is carbon a solid, liquid, or gas? Carbon, do you guys know what carbón is in Spanish? It's coal. carbon is coal. You guys ever burnt sugar? Guess what it is? And it tastes yucky, right?
Carbon.
It's carbon. That black stuff, that's carbon. Carbon is a solid. So there's some things we're assuming that you just know. And I don't think everybody knows all this stuff, obviously, right? So what about nitrogen? What is it at room temperature? Solid, liquid, or gas?
Gas.
Yeah, and hopefully we all know this is most of the stuff in the air, right? We breathe this. So yeah, it's a gas. Hopefully it's a gas, right? And oxygen we know is a gas. We breathe it. Okay? Fluorine is a
Gas.
gas. And what about the noble gases? What are they?
They're all gases.
They're all gases, right?
But they all have 8 valence electrons, which is why they are noble gases.
Okay, that's right. Okay. So what about chlorine?
Chlorine
That is a
gas.
poisonous gas. I mean, we talk about chloride in our water. So, that's not gas. It's in our water. So it's liquid. No, that's a chloride ion, right? That's different. And it all depends on what it's with, okay? So chlorine gas, well, that's a gas. What about sulfur? What's that? What would you guess? Gas?
Solid.
It's actually a solid. It's a yellow solid. Okay? And again, you wouldn't just know that, right? But sulfur is a solid. Phosphorus is also a solid. Silicon, that's a solid. Oh, I forgot boron. Boron's a solid. Okay? Bromine, that's a liquid at room temperature. That's the stuff that you put in your hot tub. Okay? Liquid.
Off topic, but bromine is really cool. It's gas. It's like a dark orange, and
Yeah.
it's heavier than air. So if you accidentally breathe it in, it's gonna push all the air out of your lungs and make you suffocate.
And am I thinking this wrong? Let me make sure I'm not telling you hogwash.
I know there is liquid bromine, but there's a gas that comes off of it that is also
Yeah.
bromine.
Oh, this doesn't tell me. Yeah. And then iodine is solid. That's probably good enough, right?
Yeah. So we just have to know.
Not on all of them. I gave you a bunch of them, so that if you knew the ones I told you, you'll be fine. Okay. All right. What about this one here? We have M. So M is a metal. And let's say we have S2. And M ion has, let's say, ten electrons. What is M? No, oh, sorry. MS3. Okay.
An ion means that it has more.
It either lost electrons or gained electrons.
And that's an S3, right?
Yeah, that's MS3, sorry.
Is it not M2F3?
What?
Is it not M2F3?
You're right. This is what happens when I try doing it in my head. Okay. This is why I tell you guys not to do it in your head, because if you're as good as I am in my head, you suck at it. Yeah. So M2S3. Yeah. So how do you do this? You split it just like the last one, right? We want to know the charge of M. We know the charge of S, it's 2 minus, right? There's 3 of them, so that's a total charge of
-6.
-6, and it's an ionic compound, so it's neutral. The other side has to be +6. Do we get this process? Okay. And there's 2 of those, so 6 divided by 2 is 3 plus. Okay, so M3 plus has 10 electrons. Well, how many did it have before it lost 3? 13. Well, it has 13 electrons if it's neutral. Aluminium, right? Are we good? That's not the one that's on the test, but can you guys do it? Any questions so far? Okay. Can you do electron geometry and molecular geometry? Do we need to go over one of these? Yeah? Okay, so let's do not one that's on the test. Let's do chlorate. ClO3 minus. So what's the first step? Count the valence electrons, right? Chlorine has 7, oxygen has 6, and there's 3 of them. And what does that negative mean?
+1.
It gained 1 more electron, right? You all with me? So that's a total of 18, 19 plus 7 is 26. Questions? Are we good so far? Okay. The central atom would be chlorine, because there's 3 oxygens, and they put them around it. And so far we have 2, 4, 6. We have 20 left, right? You with me? Am I going too fast? So where do they go? Around the oxygen. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have 2 left. Put them around chlorine. There we go. Are we done? I'd have to put a bracket and then a charge, right? Well, that's the Lewis structure. But that's not the question. The question is, what's the electron geometry and what's the molecular geometry? So what do we do once we have the Lewis structure?
We draw it in the
First of all, we count what?
regions.
The electron regions. 1, 2, 3, 4. 4 regions, so what does that tell us the electron geometry is?
Tetrahedral.
4 regions means tetrahedral, right? And what about the molecular geometry? We have 3 bonded atoms and 1 lone pair. That tells us it's trigonal pyramid. You guys have this reference sheet on your reference sheet? Okay. You don't have to, but if you don't know it, you should. Are we good there? Okay. Intermolecular forces. Do you know the 4 different types of intermolecular forces?
Hydrogen bonding is one of them.
That's one. Dipole. London dispersion, what's the strongest? Hydrogen bonding is the strongest intermolecular force for covalent compounds. If it's an ionic compound, what do we call it? Ion, right? Those are the 4.
So it goes ion, hydrogen bonding,
Dipole, and
London.
London dispersion. Yep. Okay. So going up is stronger and these are just the interactions, the attractions between molecules, right? It's not a bond, even though it says hydrogen bonding, it's not a bond, okay? And also we have increase in melting point, boiling point, right? Do you remember that? So how do you tell which ones are ion? If it's an ionic compound, yeah, metal and nonmetal. So if you can do that, you got that one, right? So the rest are for covalent. But how do we tell if it's hydrogen bonding and dipole?
Yeah. Polar.
If it's a polar molecule. Be careful on the hydrogen bonding. Hydrogen bonding is for, so what's specific about this one?
Hydrogen, nitrogen.
Hydrogen oxygen bond, or hydrogen nitrogen bond, or hydrogen fluorine bond only. If it's carbon, if it's something else, so it's not just if it has hydrogen in it. Okay, and this one is nonpolar. Are we good? So do you remember how to tell if it's a polar molecule? Do you know how to do that? Do we need an example on that?
You can tell by its geometry or its electronegativity.
Yeah. Yeah, over 0.4, so 0.5 or higher. But more important than that is its geometry. If it's not symmetrical, it's polar. So if it has a lone pair, basically it's polar. Do you know how to name covalent compounds? With the prefixes, right? Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Right?
Hold on, could you say that again?
Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. 1 through 10. Good? Do you know how to name acids? Yeah, let's do it. So acids, there are 2 types. We got binary and we got oxyacids. So how do you name binary acids? But what does bi mean? Two, right? Two elements. What's one of the element if it's an acid? Hydrogen. So hydrogen, one other element, a nonmetal. So how do you name them? For example, HCl. We use the prefix hydro, change the ending of this one to IC, chloric, and then add the word acid. So hydroic acid. Hydrochloric, hydrofluoric, hydrobromic, hydroiodic. Good? What about oxyacids?
That's the ITE.
Yeah, if the polyatomic ion, the oxyanion, right, ends in ATE, then the acid ends in IC. If it ends in ITE, then the acid ends in OUS, and we don't have a prefix. So, for example, if we have HNO3, we look at this, that's NO3, what's that? Nitrate. So it ends in 8, that means it has to end in IC. Change the ending to ic, nitric acid. Okay, all that hydrogen is telling us it's an acid. We don't put hydro in front of it. What is the chemical formula for sulfuric acid? H plus, because it has a hydrogen, right? And sulfuric, that means it's an ATE, right? So it's sulfate, SO4, 2 minus. Now what do? Cross the charges. Acids are ionic compounds. So we got H2SO4. Are we good? Questions on naming acids? Can we name ionic compounds? There's a few different types of ionic compounds. So naming ionic compounds. We got binary ionic compounds. Well, I don't know if I should call them binary. Just the main group elements. It's the metal name. And then change the ending to IDE, right? So that's like sodium chloride. Good? And then there's some like CuSO4. Has a transition metal and a polyatomic ion. How do you name polyatomic ions? Yeah, use the polyatomic ion name. So to do this, we have to find the charge of the transition metal. We know this is 2 minus. How many sulfates are there? Uh-oh, just one. Just one, because there's no parenthesis. So that's -2. This has to be +2. There's only one of them, so that's 2 plus. So it's copper, Roman numeral 2, sulfate. Are we good? You only use Roman numerals for what? Transition metals, and there's 2 other metals besides transition metals.
Alkaline metals?
No. Tin and lead. Number 50 and number 82. Good? And how I remember those are in group 4. Are you going to call them positive or negative? So they're weird, right? They're an exception.
So Roman numerals are only for metals, copper,
no,
and tin.
transition metals, the ones in the middle, and tin and lead. Okay, we kind of talked about this before when we talked about the intermolecular forces. Which one has a higher melting point or boiling point? Can you do that? What do you look at first? What's the first step to determine boiling point? And I'm not talking about the actual boiling point, but just a comparison, right? What's the first step?
Are they polar or non-polar?
Not, well, maybe. Okay. We have to tell what type of intermolecular force we have, right? Because if it's ionic compounds, ion, right? That's the strongest. If it's if it's polar, so like Charlie mentioned, then it's either hydrogen bonding or dipole-dipole. And if it's nonpolar, it's London dispersion. So whatever one has the strongest intermolecular force has a higher boiling point or higher melting point. Good? What if they have the same intermolecular force? What do we check next?
The atomic mass.
Molar mass, right, of the compound. Good? And we know how to do that by now, right? Okay.
Question is, does the lighter ones boil faster?
Nope, the heavier, oh, sure, yeah. The lighter ones boil faster, so that means the heavier ones have a higher boiling point, right? Good? Okay. And you got to know solubility. How do you know if something dissolves in water? I gave you that chart, but what if it's not like that? What if it's none of those? And say, yeah, how do you know? Like dissolves like. Do you remember that? What do we mean when we say like dissolves like? Polar molecules dissolves polar molecules. Nonpolar dissolves nonpolar. Right? So for example, we'll say, which of the following dissolves best in this compound? Whatever one is most like that compound. If that compound has hydrogen bonding, then it's one that has hydrogen bonding. If it's a London dispersion, or if it's nonpolar, whatever one's the most nonpolar, right? What if they're all polar? Which one dissolves the most in it? The one that is closest like it. For example, if we have CH4, and we want to know what does it dissolve in better? C2H6, C3H8, C4H, what is it? 12, 10? I don't know, something like that, okay? Which one does this dissolve better in? They're all nonpolar, right?
So we do it by the numbers, so like
It
C4.
probably dissolves best in that one right there. Why? Because it's closest to it. Or that's probably not a good example, but if we have CH3O and we have C2H5O, C3H7O, or something like that. And then we have C4H, I don't know these numbers, I'm just guessing here for that one. Which one does this dissolve better in? Out of these three? The bottom one.
The closest to the number.
Yeah, well, this has a big non-polar tail, this one has a big non-polar tail. Right? Things like that. Whatever one dissolves, it dissolves in the one that's most like it. Like dissolves like.
So it's a not, so like, it's a C3 or C7? H7O?
I don't know. Oh, that's a 3.
So,
But you see how this is closer to this one
yes.
in structure? Yeah. Then it's going to does it dissolve in that one too? Yes, it does, because they're all polar compounds because of that oxygen. But it'll dissolve better in that one because it's closer to it. Are we good?
Can we do it like do the molar mass of everybody and then compare it, which one is closer to that one? The molar mass?
No, you wouldn't say molar mass. It's just in structure. If they're all polar, then you find one that's closest in structure. Good? Okay. Okay, you got to know how many atoms are contained in moles. For example, if we have how many iron atoms in 5.26 moles of iron? That's just a moles to particle conversion. Can you do this? What's the conversion factor? 6.022 times 10 to 23, right? Okay, that's it. Just convert it. Use dimensional analysis, make sure you're right.
Could you repeat that, the how many moles per
6.022 times 10 to the 23 particles for 1 mole. And that's on your mole roadmap that I give you, right? Okay. You have to know how to balance chemical equations. Are we good with that, or do we need help? Yeah.
Can we go over like a hard one? I was doing the sheet, and I feel like once it gets to like, or like on the test there were like decimal ones, and I got that wrong.
Okay.
I can do that.
You don't have an example on hand, do you?
No, not a.
Okay. So let's.
Well, actually, I could.
Yeah, if you have one from your homework, that's even better, because then it's more like the one that you're considering. Because I mean, I can try to find a hard one, but hard's relative, right?
I think I was having a hard time with 36.
So the FES2?
Yeah.
Okay. So we got FES2 plus O2 gives us Fe2O3 plus SO2. All right. So where's a good place to start? Where do you want to start? Parker, where do you want to start?
Probably with iron.
Which compound should we start with?
The biggest one.
Yeah, that one right there.
Yeah.
You don't have to, guys. You don't have to remember my little tips and tricks, but it just might make it easier. So if you're struggling, get those tips and tricks down or write them down on your reference sheet, okay? So we can start with iron, that's fine, because we probably shouldn't start with oxygen, right? Because it's all over the place. And it's all by itself right there. Let's save it for last. Okay? So we got 2 irons here. How many over here? 1, so we better put a 2 there, right? Well, we just changed sulfur, so now let's do sulfur next. We have 4 on this side, so we better put a 4 right there. Do you see how I go about that? Now we can do oxygens. This side's all balanced. Well, supposedly, we have 3 here plus 8 there. Are you following? We got 4 times 2, so that's 11 here. And we have an even number here.
Okay, so can we put like a 2?
11 halves.
No.
Can we do that?
So you just put it under 2? Like always?
Only because this is even,
There.
Oh, just 'cause that's.
right? If we multiply, so 11 halves multiply 2, what's that?
22.
11. 11 halves multiply 2 is 11, right? And that's why I did 11 halves. Okay? So that it's the same on this side. Now it's all balanced, but we can't leave it as 11 halves, can we? So how do we get rid of this denominator?
Just put over 2.
Multiply by 2. Which one? What else do we have to multiply by 2?
The 11.
Everything. If we multiply everything by the same number, it's still balanced, right? And so that's going to be 4FeS2 plus 11O2 gives us 2Fe2O3 plus 8SO2.
Okay.
Does that make sense?
Yeah.
So if you can balance it with fractions or decimals or whatever, then do it, and then try to get rid of that fraction or decimal.
Would it be possible to do it by least common denominator?
Yeah, probably. But I wouldn't want to do that, because then you'd be going back and forth, back and forth, back and forth. You're like, oh, I change it here, and then it changes here, then it changes that over there. You see what I mean? So if everything's balanced except for 1, and it's like, if you're doing least common multiple, it's good to do that one first.
Okay.
But you might not see it at first. But if you do see that, then yeah, do least common multiple. But oxygen's everywhere, that might be hard to see. Yeah, Parker.
So on the unit 4 test, it had you it gave you an equation, and then you had to pick what coefficients,
Uh-huh.
in order on each of them. And they had decimals in them, and I thought they couldn't be decimal.
They only have the option for the decimal, but the answer is not.
But they were right. Oh, okay. I got it wrong, so.
I saw the decimal.
Oh, okay.
Yeah. So yeah, you never leave it with a fraction or decimal.
So you could just
Yeah.
leave those off.
Yep. But make sure you know, don't just, it's not that one, because there's probably still other ones, right?
Right.
So just, yeah. Are we good with balancing? Okay. Okay, now we got stoichiometry. Should we go through an example of this? Okay. So let's say we have, I'm just going to, sodium plus water gives us sodium hydroxide and hydrogen gas. Okay. What's our first, let's say we have 3 grams of this and 3 grams of that. And we want to know how many grams of H2 are we going to make? That's our question. Okay? What's our first step? One step before we do that. Balance the equation. You have to have a balanced equation. Is this one balanced? Not quite. So we need a 2 right there. Hold on. Is that right?
And 2 H2O.
And 2 right there. And 2 right there. All right? Okay. So we got a balanced equation. And now we got to do what? Convert which one to mole? 3 grams of sodium or 3 grams of water? Yes, both of them. Just do one at a time. So 3 grams of sodium and convert it to what? Grams of H2, because that's what we're looking for, right? So what do we do first? Grams to what?
Moles?
To moles, like Vita said, of Na, and write everything down. So 23 grams to 1 mole. Does everybody understand how we got that? Molar mass of sodium. Okay. So grams goes away. Now, what goes on bottom? How many? 2 moles of sodium, so that cancels moles of sodium, right? And we're going to moles of H2. That's what we're looking for. So how many? What goes on top? 1 mole of H2. Are you all with me? Questions? Okay, so that goes away. And we got to go clear to grams. So for every 1 mole of H2, goes on bottom, so they cancel, right? And what's the molar mass? 2 grams of H2. And we're left with grams, and we get an answer. What is it? 3 divide 23 divide 2 multiply 2 is tiny number. Somebody. Nobody? Zero 0.1304. I'm not going to round till the end. Grams of H2. Are you with me? Okay. And now we do 3 grams of water and convert it to grams of H2. What's the molar mass of water? 18 grams, right, per 1 mole. Do you have to memorize that thing, guys? No, just know how to calculate it. You with me? Am I going too fast? Okay, what's the mole-to-mole ratio of water to hydrogen gas? Somebody tell me. 1 mole of H2 to every 2 moles of H2O. Does everybody get that? Right here and here, right? That's why you have to have a balanced equation, guys. So that goes away. And we're just going to copy and paste that. 2 grams of H2 every 1 mole of H2. That goes away. And we're left with 3 divide 18. 0.167 grams of H2. So what's our answer? How many grams of H2 do we make? What's our best prediction? Right here. Why? It's the smallest amount. This means our sodium is our limiting reagent, right? Our limiting reactant. Are you with me? And you have to be able to say how much excess reagent we have left over. How much of this do we have left over? Our water is our excess reactant. Are you with me? Okay.
So would we subtract the 0.1304
Nope.
from the 2, or from
Nothing like that.
Ah,
So we're not going to use this at all, right?
right.
We're not going to use this to find out how much leftover we have either, because this is H2. Our excess reagent is H2O. So that's like adding apples and oranges if we try to subtract that from something. So we start again with this. Why do we start with sodium? Because that's our limiting reactant. We start with 3 grams of sodium and we figure out how much water we actually need. So we're going to do the same thing. So 1 mole of sodium to 23 grams of sodium. And then convert moles of sodium to moles of water. It's a 1-to-1 ratio or 2-to-2 ratio. 2 moles of sodium to 2 moles of H2O. And then keep going. 1 mole of H2O has a mass of 18 grams of H2O. Did I go too fast? Tell me, please.
A little, could you back it up to, the 2 moles of H2O, 2 moles?
So do you understand where I got that?
That one?
2 to 2.
Oh.
Right, whenever you're going from moles, use your mole roadmap, guys. Whenever you're going from moles of one substance to moles of another substance, you got to use the coefficients on our balanced equation.
Would it trouble you terribly to redraw the molar roadmap?
No, but it's on that sheet that I gave you. No, on that reference sheet that I'm going to give you. Do you have that one still with the electronegativity chart? And so if we do this, we got 3 divide 23 times 18, and then the 2's cancel. We got 2.35 grams of H2O. That's how much we need. So how many do we have left over? How do we figure that out? We start with 3 grams. Oops. Uh-oh, that was weird. Uh-oh. I deleted everything I just did. Well, it's gone. Let's see if I don't know how I did that. It's gone. But so it's 3 subtract, what was it? 2.3 something? 2.35? So that's going to be what? 0.65 grams of water left.
Yes.
Does that make sense, everybody? You're going to have to be able to do all that stuff. Okay, we're just about out of time here. Well, we got 8 minutes left. So, been going through everything. Let's make sure we got the rest of it's probably the most recent stuff we've done. Okay, so we have okay, that's good. Limiting reagents. Can do that, right? We just did that. Percent yield. Can you do percent yield? Do we need to go over that? It's what we actually get divided by our theoretical yield. This is our theoretical yield, right? And then times by 100. Good. And then molarity. Can you determine molarity? Moles over liters. If you're not given moles, you're given grams, you convert grams to moles, right? If you're not given liters, you're given milliliters, then you kind of convert milliliters to liters, right? Got to know it's moles over liters. making a dilution. What's the equation for dilution? M1V1 equals M2V2. Write that down. Do we have any questions with that? If you want to go over it, I can. I'll go over as much as you want. We just have 8 minutes left. No? Okay. So you've had this on critical chemistry. They'll give you like a list of ions. And they'll say, which of the following will form a precipitate? Do you understand what I'm asking? So if you have Na plus, Cl minus, OH plus, and let's say Ag plus, and NO3 minus, I don't know, whatever. Which combination will form a precipitate? You look at that chart that I gave you, right? That solubility chart?
Mm-hmm.
Yeah, which one?
You say like combination of it?
Yep,
Cl minus and Ag.
that's it. Because chloride is soluble except with silver plus, right? This one is always going to be soluble. So it's not that one. It's not that one. That one's always going to be soluble. And that's not a plus, that's a minus. My bad.
So precipitant is like oil and water in that it doesn't.
No, a precipitate, it means it is insoluble in water. It doesn't dissolve. It'll form a solid. Remember that. Was you here that time that I did the demonstrations? With the, okay. All right. So you look at that solubility chart. You can rewatch the video and get that. Writing the net ionic equation. Can you do that? If you have a question, let me know right now.
What was it?
Net ionic equation. Yep. So if we have, let's say PbNO3, this is the one we did in class. Ki gives us KNO3 and PbI2. And if we look at the solubility charts, this is aqueous, right? This is aqueous. That means it dissolves in water. This is aqueous, and this is a solid. So we got to write a net ionic equation here. So the easiest way to do this, what is our product? What is our only product here? Lead iodide. Is this a product? It's not. Why isn't it? Because it's still dissociated, right? It didn't really form that. This is just a prediction, okay? So PbI2 is our only product. And how do we get that? From Pb2 plus and I2 minus. Sorry, not 2 minus, 1 minus. Is it balanced? No, we better put a 2 right there. Did I go too quickly?
No, I think I got it. I think I was in the, I got a little bit left in the lesson on this one.
Okay,
So I will get it once I
all right.
figure out it.
Did that make sense to everybody? I'm trying not to go over time, and maybe I shouldn't be, and just slow down, right? Are we good with net ionic equations? So we have to write the ions, the charge. That's why it's an ionic equation, okay? And how to tell if it's acid-base reaction, precipitation reaction, or redox reaction? If it has a solid from two aqueous solutions, it's a precipitation reaction. Good? How do you tell if it's an acid-base reaction? If it has an acid and a base. How do you tell if it's an acid? H plus is the cation, right? How do you tell if it's a base? That's the anion, OH, right? For this class, that's all you need to know.
H plus is what?
This is the acid. Remember when we talked about naming acids? Has a H plus, the H is the cation. And if it has a OH minus, a hydroxide as the anion, that's a base. And if it has both an acid and a base, then it's an acid-base reaction.
So they're acid-base, precipitant, and
Redox reaction, oxidation reduction reaction. Yeah, how do you tell if it's an oxidation reduction reaction? Yeah, if it's not a double replacement reaction. And the acid base and precipitation reaction are both double replacement reactions. Good? Okay, mass percent. Or so it's really basically percent composition on this one. Can you do that? Okay. And then determine the empirical formula. Can you do empirical formulas? Does anybody need help with that? Anybody? Okay. What about molecular formula? Need help? Or you got it? Okay. That's it. Do we have any questions? So I went through the entire exam. Do we have any questions on anything? Because anything's like, oh, that's still. And let me tell you, if you want to go, because it's time, overtime, 1 minute, sorry guys. If you want to go, you can go. If you want to stay, I'll stay for a bit.
If I have a question, can I email you on Wednesday?
Depends on if I'm asleep.
So like before 5 p.m.?
No, you can email me and yeah,
Okay.
I'll be sure and check.
I'll try to keep it within the typical like 9 to 5 hours.
Well, if not a problem, you can email me in the middle of the night. I don't care, but
You might
I
not
just
look.
might not look at it because Wednesday night is right before the test, right?
Right.
Yeah, I'll try to look at it Thursday morning anyway. Anything else? Okay, study, study, study. Let's ace this thing. Some of you aced the midterm. Let's see if we can ace that final. And if you guys have any questions, please email me. Yes, sooner the better. I wasn't saying I wouldn't respond. I'm just, if it's not enough time, I might not be able to get to you in time. Hold on. Are we good with the e-portfolio?
Yeah.
Okay. The last day to turn anything in should be when?
August 1st?
August 1st is the day we're taking the final. Is that the day you want it? I think grades are due by, is it the 7th or is it the 5th? I think it's this.
I think it's the 7th online because that's my last day to take.
Yeah, let's say by the 6th. Everything in by the 6th. Sound good? Okay, if you have any questions, I'll be available until the 6th. email anyway. Good? Okay, have a great day and be ready for that final study. Bring your reference sheet. Make sure it's updated.